or just touching back on the last slide that we looked at, all of this is one cardiac cycle. From the point that we start, that SA node starts the firing, up to the point that conduction travels all the way down to the Purkinje fibers, and that SA node fires again approximately 0.6 seconds later. So every time that SA node fires, that starts the heartbeat. And that's exactly what you guys are going to be doing later in the lab, is you're going to be counting the waveforms. But it's not going to look like this. We've got to go into what ECG readings are in a couple slides over. So as I said, this heart doesn't have any central nervous system stimulation taking place. It can fire on its own, and the SA node fires at 100 beats per minute. But that doesn't mean that this heart is not under autonomic regulation. It is. So in fact, our hearts aren't beating at 100 beats per minute all the time. They're continually adjusting based on the amount of sympathetic output and parasympathetic output. So this is going to tie back into our lecture that we looked at when we looked at our peripheral nervous system lecture, specifically autonomic regulation. So looking at the pathways, we know that the medulla oblongata is going to contain nuclei that are going to be responsible. It's going to be receiving sensory information about, which I'll talk about in the next slide over. It's going to be receiving sensory information about the state of our metabolic needs. It's going to measure the heart. It's going to measure the output, the flow of blood through the heart. It's going to measure blood pressure. And all of that is feeding into the medulla oblongata, which are going to contain two specific nuclei. We're going to have a cardio-acceleratory area, and we're going to have a cardio-inhibitory area. And those areas are either going to speed up the heart or slow down the heart. And if we take a look at the, let's start off with the cardio-inhibitory, so parasympathetic output. Parasympathetic output that starts from the cardio-inhibitory area, we're going to see the dorsal motor nuclei of the vagus nerve travel out that nuclei of the cardio-inhibitory center, travel out. You're going to have a long, this is a pre-ganglion neuron, a long pre-ganglion neuron, axon, that's traveling all the way to the ganglion close to the heart. So there's going to be our ganglion, our parasympathetic ganglion that's close to the target tissues, and we're going to have our short post-ganglion axons that travel from the ganglion out to the SA node and the AV node. And that should make sense, because these areas, the SA node and the AV node, the SA node is the pacemaker. It's the one saying, we beat at 100 beats per minute. So this vagus nerve is the one, cranial nerve 10, travels all the way out and innervates those two pacemaker areas. If we're going to take a look at the cardiosympathetic, or the cardio-acceleratory area, again, that's going to travel out from that nuclei. That's going to innervate the spinal nerve area that innervates the heart. We're going to take a look at where this starts off at. It's going to start off at the lateral gray horn. Not the dorsal gray horn, because the dorsal gray horn, the ventral gray horn is going to be somatic. These are going to be our autonomic areas. The lateral gray horn all the way out the sympathetic trunk ganglion. Sympathetic trunk ganglion out is going to be our long post-ganglion axons that terminate on the SA node. The AV node, as well as the ventricular muscles. So you'll note that the effects of that, if we get excitation of the sympathetic pathways to the heart, we're going to stimulate a higher depolarization rate, meaning we're going to increase the pacemaker potential of the SA node and the AV node to fire at an even faster rate. Now, the parasympathetic output does the exact opposite, where it's going to innervate the SA node and AV node, and parasympathetic is going to slow that down. So remember, parasympathetic being rest and digest. So we want to bring that back down from 100 beats per minute down to about 60 to 70 beats per minute. The only difference between the two is that the sympathetic output targets ventricular muscle mass, and something that we'll learn later, it'll also affect the vessels as well, the veins. So looking at all of this, they have, and let me talk about what's taking place on the next slide over. all of this, the adjustments that are taking place on the heart rate at the SA node as well as the AV node, the sympathetic pathways, and all of this is written out for you guys on the next slide over. Sympathetic output, you would basically know that the postganglion neuron that targets the heart muscle are going to be secreting what neurotransmitter? Again, sympathetic pathway, postganglion neuron is secreting either epinephrine or acetylcholine. Which one is it? Which one? Acetylcholine? Remember, these are going to be adrenergic receptors on the SA node and AV node. So if they're adrenergic, they're going to be secreting epinephrine. So sympathetic pathways, remember, sympathetic pathways, epinephrine. If I want the heart to beat faster, remember what I mentioned about Pulp Fiction. They took that needle filled with epinephrine, adrenaline, and stabbed it into her heart. And that caused the heart to start beating faster. So the neurotransmitter that's released is epinephrine. If you were to take a look at the parasympathetic pathways, the postganglion neurons are going to secrete acetylcholine. So depending on what you actually just sprinkle on the SA node and AV node, if you sprinkle epinephrine, that's going to raise the heart rate. If you sprinkle acetylcholine on the AV node, that's going to slow it back down. And tons of these studies have basically done that with hearts. What things can we put in that comes in that will speed up the heart? One of the things that I mentioned earlier, SA node fires at 100 beats per minute. And they know that because one of the earlier studies that they used to do was they used to cut the vagus nerve on dogs. And by cutting the vagus nerve, we know that's the parasympathetic output to the heart. And intrinsically, what happens to the heart rate for dogs? It was 70, brings it right back up to about 100. So cutting off any of what we call vagal tone, so the vagus nerves provides vagal tone, which decreases the heart rate back from 100 beats per minute down to about 60 to 70 beats per minute. So what we're looking at, the set point, we're starting off at 100 beats per minute. To bring it down to about 60 beats per minute is vagal tone, or parasympathetic output. To raise the heart rate up to about 200 beats per minute would require sympathetic output. That's epinephrine. So right now, all of us are sitting presumably with a heart rate between 60 to 80 beats per minute. You do have vagal tone. That's your parasympathetic output saying you're resting, you're digesting. We don't need you at 100 beats per minute, so let's slow that back down to 60 beats per minute. Now, let's say something were to happen right now, knock on wood, but all of a sudden it's going to cause us to fight or flight. We're going to have to get up and start running. So what's going to happen? Parasympathetic output is coming in, and it's already working on the heart. Event happens. Now we're going to turn off the parasympathetic output. That's going to raise us back to 100 beats per minute, and then sympathetic output starts to increase to raise us back to a higher rate. So what that means is that your heart is undergoing a certain amount of sympathetic output and a certain amount of parasympathetic output, and it's working together to balance your heart rate at a resting heart rate of about 60 to 70 beats per minute. It's not until you want to raise it back up to about 100 beats per minute that you turn off the amount of vagal tone. And depending on your stress levels, depending on the amount of cortisol, depending on also how well your heart efficiently pumps blood, it's going to be dependent on what your beats per minute is, or your heart rate is at intrinsically. So the next slide over, all of this that we've been talking about is the efferent pathway. This is the efferent pathway from the medulla oblongata out to the heart. But what we do need to talk about is the sensory information. So we've talked about the first portion. Now we'll talk about What's sensory information? And here you can see our integration center, the integrative function of the whole sensory, integrative, motor pathways. Motor pathways we already described earlier. Cardioaccelerator is going to increase the rate of depolarization of the SA node. It's going to also increase contractility of the ventricles. If we look at parasympathetic output only decreases the depolarization of the SA node as well as the AV node. So decreases heart rate. We've already talked about that. The sensory input that comes in and feeds the medulla oblongata, we want to be able to receive information about the amount of blood that's flowing through the system. So the areas that we probably would want to stick those sensors in to help us adjust the amount of blood flowing to those areas would probably be the aorta. Probably makes sense because that's our direct output for systemic, is our direct systemic output. And probably some other receptors leading up to the brain itself. So the carotid body's located. That would probably be good areas. So where do we see these baroreceptors? Baroreceptors detect the amount of pressure, the blood pressure in those areas. And by the amount of pressure, we can also determine the amount of volume and flow of blood through those areas. So it's all related. Volume, flow is all related to pressure, something we'll learn in our respiratory lecture. And actually this lecture as well. So we want to make sure that the pressure is appropriate because that pressure is going to be important for blood flow throughout the systemic circuit, which includes blood going up to the brain. So we want to make sure we got enough pressure, enough blood flow to the critical organs. So naturally those baroreceptors are located in the aorta as well as the carotid bodies. What other information leads into the medulla oblongata from other brain centers? You got your cerebral cortex. Your primary motor cortex is saying, I'm doing a lot of movement right now, so you probably want to ramp up the heart a little bit. That's going to lead into the medulla oblongata, specifically into the cardioacceleratory areas. Your limbic system is going to be involved in emotions. You start to get really emotional, start getting a little angry, you start raising your heart rate back up. Looking at the other sensory receptors that are located. Baroreceptors, which we already mentioned, which detect pressure in those areas, aortic arch as well as the carotid bodies. Chemoreceptors are also going to tell us the state of chemicals in the blood. Is the CO2 too high? Is our oxygen levels low? Do I need to start increasing blood flow through the heart? Am I starting to detect the presence of excessive hydrogen ions? Maybe increased acids are forming in the blood, decreasing the pH of the blood.
Do like drugs affect chemoreceptors?
Down the line, yeah. There can be, looking at those pathways can actually start to, keep in mind that those pathways start to affect the amount of catecholamines in the system, so the amount of epinephrine. So those things could actually start exciting brain activity that could tell the cardiovascular regions to start ramping up. They might not directly affect the medulla oblongata, and that I don't know, but they'll certainly have an effect somewhere up in the central nervous system, because it's a central nervous stimulant. If you look at speed, which is an amphetamine, will stimulate central nervous system, which will then feed into the cardiovascular center. That targets our chemoreceptors, so any hydrogen ions that would lower the pH, like metabolic acidosis, the production of lactic acid. Right? Those types of receptors will say you may want to speed up the heart again. The other thing on here that you'll see, proprioceptors, things involved in motion. So any movements that take place, again, feed into the cardiovascular region to say ramp up, you gotta increase your blood flow, therefore you need to increase the heart rate. So the other things to look at in this table, as you know, I really like my tables to help kind of sum up all that information. you can see the SA node, AV node, and ventricular conduction pathway are all going to be related to the pacemakers. The atrial muscle down to ventricular muscle are going to be our muscle cells. And this is the effect of parasympathetic and sympathetic stimulation. So we know what's going to happen with vagal tone. Vagal tone is going to decrease the SA node and AV node. It's going to, parasympathetic output, even though I didn't say it doesn't really have an effect on muscle, it has a slight effect on the atrial muscles, so don't worry about that. All in all, if I were to ask you about vagal tone, predominantly going to affect the pacemaker cells. Sympathetic output is going to increase the rate of depolarization of the SA node and AV node, and it's also going to increase the strength of the contraction. So that sprinkling of epinephrine and norepinephrine on the heart itself will affect the intrinsic rate of depolarization in the pacemaker cells, as well as the strength of the contraction. Because that's going to contribute to a concept that we'll talk about at the end of, on the beginning of Thursday. Not only do I want my heart to beat faster, I also want the heart to be stronger. Okay? I want to increase the amount of blood that's ejected in that heartbeat. And that example is going to be both the combination of the heart rate as well as the amount of blood ejected per beat is going to be a concept we're going to call cardiac output. It's how much blood is flowing through the heart itself. And if you don't believe me, do something. If you can sort of feel your heart, maybe not now, at some point you want to feel yourself later on. If you want to feel your heart later, during exercise, you'll feel your heart thumping out of your chest. Not only is it beating faster, but it's beating stronger. We want to be able to increase the amount of blood flow. That's our cardiac output. Again, something we'll save later on. Summing that all up, increased contraction of the atrial as well as the ventricular muscle due to sympathetic output. And that, again, can be visualized based on this right here. Sympathetic output to the muscle cells. With that, we will move on to the next slide. So what we've again talked about the entire, in the last couple slides over, are the action potentials that are generated in the heart. Out of looking at the amount of mass in the heart, the SA node being a couple millimeters squared in surface, in volume, and the AV node and the other branches being a couple millimeters squared or cubed in volume as well. The majority of all the cells in the heart are mostly muscle cells. Wouldn't you agree? Yeah? Okay. So mostly muscle cells, almost all entirely muscle cells. If you were to measure the activity going on, and again, going back to our action potential for the cardiac muscle cells, you would probably see that the most activity that would be measured would be taking place with the cardiac muscle cells. And we know that these cardiac muscle cells beat, depending on where they're located, where the atria or the ventricles, beat at different times. So what we're going to be doing for the ECG, what exactly is the ECG? It's our electrocardiogram, also known as, how many people still refer to as EKG? Probably a lot. What is it? What is EKG? It's electrocardiogram in German. EKG, but here we call it ECG. So you may get corrected if you ever call it an EKG. It's called an ECG because we call it electrocardiogram. And what an electrocardiogram does is it just basically measures the changes in membrane potential. So if I were to measure a cell, I've got my lonely cell here, and I'm just going to measure the changes that take place from resting membrane potential, I'll notice I'll have my depolarization, I'll have my extended depolarization, and then I'm going to have my repolarization. This is measuring the changes that are taking place in terms of negative 90 millivolts. These are absolute changes that are taking place, so about 20 millivolts. We want to measure any changes when the cell is at rest. So when a cell is at rest, and here we can just draw it as a 0. When you see a heart cell and there's no changes in the membrane potential, it'll be a 0, right? And so if it stays 0 the entire time, that means the heart cell is not working, it's not beating. But that's not what's taking place. You saw in the very beginning a huge rate of change in the depolarization. So we would expect, right at the very beginning, here we see our cell at rest. Let me just draw this in blue. Here we see the heart at rest. And I'm just going to draw, let me draw that depolarization curve right up on top. Can you guys see that? Kind of. Okay. So here's our depolarization curve at the top. We see the biggest change taking place in the very beginning. So we would expect to see a little bump. Oh, stop. Somehow I ended my... Sorry, just give me a sec. All right, let's just start over. Sorry. Okay, so I'm going to start over with, which is good because then I can kind of redo what my thing looked like. I'm going to draw my depolarization curve up here at the top. Here's at negative 90. Here we are at rest. And then I'm going to draw my depolarization back down and back down over here. So this is my cardiac muscle. Let's just call this, let me just make it easy. Let's call it our ventricular muscle. Now, measuring any changes that are taking place, I can draw out on our graph, which is going to measure any changes, the rate of change of the depolarization and repolarization that's taking place during muscle contraction. So the change taking place at the initial portion, which I'm going to draw in blue, it's going to stay 0, right up at that point in time. Right here we see that large depolarization that takes place. So I see a huge change taking place. If this is depolarization, what I should see is a little blip. And then, once it reaches the very top, it slows down, and then the change from this point on, is there any changes taking place from this point at the top? No. So it should even back out. When does the next change take place? During repolarization, where you're going to see now a change in the membrane potential, so you should expect to see another blip. And then it evens out. So everything here, this is going to represent the depolarization, and this is going to represent the repolarization, which are going to represent huge changes in the membrane potential. That's exactly what an ECG does. It measures when those changes occur. So if you were going to take a look at the ventricles, you'll see a blip when you see depolarization. You see another blip with repolarization. So now let's draw that out. Let me draw what this would look like with both atria and ventricles. So the first thing you would expect to see is the blip with the atria. The atria we know, the SA node fires, the atria contract. Again, atria being, at least looking just at the muscle cells, we want to be able to measure the muscle cells changes in the depolarization and repolarization. So we expect to see a little blip first, which is going to be atrial depolarization. And then, what would be the next blip? If I had atrial depolarization, what's the next one? Atrial repolarization is the next blip. Then, what's the next thing I should see? What contracts after the atria? Ventricles. So the next blip I should see, ventricular depolarization first, right? Then the next blip I should see, ventricular repolarization. So it should look like this. But technically our ECG doesn't look like this. It looks combined. The first bit you see is what's called our P wave. And our P wave, and all of this is described on the next slide over. Okay, I'll do it off this one. The first thing that you're going to be able to see is the first blip would be atrial depolarization. It starts off with the SA node starting, and you're going to see the waveform, the movement of our sodium ions moving through the cardiac muscle cells. You see the first portion, now that wave spreading. This is our depolarization. It's the start of contraction, which is marked in yellow. The next blip you're going to see is when the repolarization starts, which is down over here. And it's not until you get to this portion right here where the atrial relaxation finishes or starts. And atrial relaxation is depolarization that takes place. Let me rephrase that. Repolarization. So let me go back to this portion right here. P wave marks the start of atrial depolarization. This point is where atrial repolarization takes place. At the same time, after atrial repolarization takes place, there's another thing that takes place, which is ventricular depolarization. So in essence, what this is doing, it's creating one big blip. Because not only am I getting atrial repolarization, I'm also getting ventricular depolarization. So I'm getting a lot of changes that are taking place in the atria as well as the ventricles. So that's going to be combined. First is going to be your P wave, then this whole segment right here is called the QRS. And the R wave is the biggest deflection that you see. And that's the start of ventricular depolarization. Now, the last portion, which you guys described, is ventricular repolarization, which is exactly what T is. And while you guys are all writing that down, I got that all for you right over here. Next slide. So this is going to be important because what we can do from here, why this ECG is so important, again, it's measuring the changes. Take a look, it's millivolts, changes in millivolts that's taking place. 0 when the heart hasn't started its cardiac cycle. At the start of the cardiac cycle, P represents atrial depolarization, then we go into atrial repolarization. At the same time, ventricular depolarization takes place. The reason you don't see a separate blip is because the ventricular depolarization masks atrial repolarization. Then, that last segment would be ventricular repolarization. Those three big waveforms and all the time points in between tell us exactly the timing of the heart. The time that I can see, which is our PQ interval, if I were to note where the big segments are, and let's take a look at that on the next slide over, this slide over, because this just expands on everything. P is atrial depolarization. Let's start from R. R is QRS. This whole segment from QRS to about T, which they actually call the ST segment. The ST segment, let me draw that up. From QRS marking the start of ventricular depolarization, all the way to about T, which starts the beginning of ventricular repolarization. That entire length right here is ventricular systole. That is the time of ventricular contraction. So that segment right there, the ST segment, is important because during ventricular contraction, especially the latter portion of ventricular contraction, signifies the amount of time that it takes for the ventricles to squeeze and empty the blood out. An ST segment is extremely important because what happens if you see somebody's ECG and the ST segment is short? That means that the ventricle did not have enough time to empty out completely before ventricular repolarization takes place. Hence why ST segment is extremely important and something that they want to look at in an ECG. If you don't have enough time to empty out the ventricles, well, you're not completely emptying out the ventricles, but if you can't get enough blood out of the ventricles, that means that's not enough blood flowing through the systemic circuit. So you've got reduced output out of the heart flowing through the ventricles, not providing enough blood. And they can see that just off a bunch of electrodes placed on your chest. The other thing that we look at is the PQ interval. PQ interval, again, between atrial, the start of atrial depolarization to the start of atrial repolarization, is the amount of time for the atrial kick. Atrial kick is atrial contraction. Can the ventricles be filled up during, if this were systole, if all this is systole, the rest is ventricular diastole. And that's the time that ventricles are relaxed. Is there enough time in the PQ interval? Is the PQ interval appropriate enough? Is it long enough to be able to fill the ventricles up? Because it's one thing if during the ST segment, can the ventricles squeeze enough blood out? But can it also be filled by the atria during atrial systole? So these are the things to consider when you're looking at an ECG. You can just measure the times because frankly, the ECG waveform is fairly standard. You've got machines that you plug them in, and they will measure what the reference intervals are based on your age, your gender. It knows what normal values are for PQ segments. It knows the length for ST segments. And especially measuring this over changes, let's say at times, let's say when, and this is the reason why they do stress tests, they do treadmill tests with ECGs. They want to see how does the heart respond, not only at rest, but also when you're performing any form of exercise. Let's say you're out, and it doesn't necessarily have to be like a marathon you're running. These could be things that increase your heart rate. Does your heart operate normally with increased sympathetic output? Are there any changes in the ST segment? And any changes that deviate from normal basically mean inefficiency of the heart. Either the inability to fill completely or the inability to completely eject the proper amount of blood. So those are the things that I'd like you guys to be very familiar with. Again, looking at the ECG, measuring the rate of changes that are taking place. And all of that is broken down. When you look at the phases of the ECG, we'll do exactly this for you. They'll pinpoint the start of atrial depolarization, repolarization that's starting to take place, the conduction moving down to the Purkinje fibers, and then this huge waveform is the start of ventricular contraction or ventricular depolarization, and then this will relax at our T wave at the very end. Each of that is broken down for you, going through each of these segments taking place. So take that and make sure that you move through each of the segments to see when things are taking place. Again, systole marks the time from depolarization to repolarization. Here you can see where ventricular systole takes place. This is atrial systole. Everything else outside of this is ventricular diastole. Now we know what's happening with the muscle cells, that we've been able to sum that up. Let's take a look at a video that will, got two videos. Just give me a second, I'm trying to figure out how far we can go. 3 minutes and 45
The
seconds.
cardiac conduction system consists of the following components. The sinoatrial node, or SA node, located in the right atrium near the
Good videos I
entrance
think I
of the
posted on
superior
Canvas
vena
that you guys can
cava.
watch also in the
This is
Google
the
Drive.
natural pacemaker of the heart. It initiates all heartbeat and determines heart rate. Electrical impulses from the SA node spread throughout both atria and stimulate them to contract. The atrioventricular node, or AV node, located on the other side of the right atrium near the AV valve. The AV node serves as electrical gateway to the ventricles. It delays the passage of electrical impulses to the ventricles. This delay is to ensure that the atria have ejected all the blood into the ventricles before the ventricles contract. The AV node receives signals from the SA node and passes them onto the atrioventricular bundle, AV bundle, or bundle of His. This bundle is then divided into right and left bundle branches, which conduct the impulses toward the apex of the heart. The signals are then passed onto Purkinje fibers, turning upward and spreading throughout the ventricular myocardium. Electrical activities of the heart can be recorded in the form of electrocardiogram, ECG, or EKG. An ECG is a composite recording of all the action potentials produced by the nodes and the cells of the myocardium. Each wave or segment of the ECG corresponds to a certain event of the cardiac electrical cycle. When the atria are full of blood, the SA node fires. Electrical signals spread throughout the atria and cause them to depolarize. This is represented by the P wave on the ECG. Atrial contraction, or atrial systole, starts about 100 milliseconds after the P wave begins. The PQ segment represents the time the signals travel from the SA node to the AV node. The QRS complex marks the firing of the AV node and represents ventricular depolarization. Q wave corresponds to depolarization of the interventricular septum. R wave is produced by depolarization of the main mass of the ventricles. S wave represents the last phase of ventricular depolarization at the base of the heart. Atrial repolarization also occurs during this time, but the signal is obscured by the large QRS complex. The ST segment reflects the plateau in the myocardial action potential. This is when the ventricles contract and pump blood. The T wave represents ventricular repolarization immediately before ventricular relaxation, or ventricular diastole. The cycle repeats itself with every heartbeat.
Hopefully that helps sum all that up for you. The next video, let's see if that warrants any. I believe I posted this as well. Basically just post the same thing, so you guys can watch that on your own time. So now what we've talked about the electrical activity of the heart. We've talked about and this is specifically looking at the ventricle, the ventricles. We see the ventricular action potential in purple. We see the electrical activity of the heart, which you can see our ECG on the bottom. What we do need to now take a look at are the changes in pressure that take place as a result of the contraction that takes place. Now in this slide, what we can first start off with is pointing out where, and I believe I go over this later on. Oh yeah, okay, you know what? That's okay. I just want to show you how complicated it's going to get. So here you're going to be able to see the pressures taking place. This is going to be part of the diagram where, at least let me just finish up my sentence. We can start off by in preparation for Thursday is to note where ventricular systole takes place. So this marks ventricular systole. You can see that taking place with the ventricular action potential. We're going to want to take a look at the changes in pressure that happen in the ventricle as well as the aorta. So that whole example that I talked about, where this was the heart, that was our aortic valve, that door, and outside was the aorta, are all going to be relating the pressures that are taking place during ventricular diastole to ventricular systole, which we mark off as QRS, and then the T wave, and which we can see also taking place up on our purple line, the beginning of depolarization to the beginning of repolarization. And seeing the pressures that are taking place, and let me give you the summary of what's taking place. The left ventricular pressure during ventricular diastole is close to 0, about 0 to 5 millimeters of mercury. Right at the very beginning of ventricular diastole, ventricular systole, is the marked increase in pressure. So remember what I was saying earlier is ventricular muscle walls are contracting. You see the pressure rising. Now the measurement of the aortic pressure is the back pressure exerted by the aorta on the aortic valve. So in order for us to open that door, we have to be able to generate enough pressure to exceed 80 millimeters of mercury of pressure. So what's going to happen is the pressure keeps rising. The volume doesn't change, and this graph doesn't even show you volume. That's something I'll show you in Wigger's diagram. The pressure starts to increase, keeps increasing, up to the point that the pressure now matches, the pressure in the left ventricle matches the aorta. So in that example that I mentioned earlier, you have 80 millimeters of mercury being exerted by the aorta onto the aortic valve. You have now 80 millimeters of mercury of pressure pushing up due to ventricular contraction or ventricular systole pressing up against the aortic valve as well. The second that aortic, the ventricular pressure exceeds that of the aortic pressure is where you start to see blood flow taking place. And blood flow is now being ejected. Remember, this is still continued contraction. We get blood flow being ejected out of the left ventricle. And the peak that it reaches is 120 millimeters of mercury. Up until the point, now we're at relaxation, and now the pressure starts to decrease. Decrease. And we're going to start to decrease up to the point that the aortic pressure is going to be higher than that of the ventricular pressure. So this marks the point at which the aortic valve closes. This portion, not that portion, this point right here marks where the aortic valve opens. So this whole point right here represents, from here to here, measures the amount of blood that's ejected by the ventricles when the aortic valve opens to the point it closes. You'll see pressures drop. Why? Because we're in ventricular diastole. And then pressure comes back to normal. So like I said, that's going to show you a taste. We're going to add on to this the actual pictures of the cardiac cycle, as well as pictures of ventricular volume. And we'll save that for the beginning of Thursday. So in order for you guys to get acquainted with that, review this slide, because we're going to add to that. So looking at ECG abnormalities, now that you have an idea of what's taking place in terms of the ECG, the ventricular action potentials, and the pressures, which we'll worry about later. Any deviance from our blood pressures. Our heart rate. Heart rate should be about 60 to about 70 beats per minute. That's about your resting blood pressure, resting heart rate. And looking at the terms that you probably would have been seeing at some point, bradycardia is a slow heart rate, less than 60 beats per minute. Tachycardia is a fast resting heart rate, so anything above that 100 beats per minute. Typically, things that you would see with bradycardia, if people have a slow heart rate, people will exhibit low blood flow to to the rest of the systemic circuit. So people typically will feel some fatigue, feel weakness, sometimes dizziness, low blood pressure to the carotid bodies. The exception to that would be athletes. People that have a tendency to be athletic will have lower heart rates than 60 beats per minute. Why? Because the heart is it's a muscle. It can completely empty. So something that we'll explore the notion later, which is cardiac output. It's not entirely related to heart rate, but it's heart rate times the term which we'll talk about, stroke volume. Athletes have a tendency to be able to fill blood more in their left ventricle, and they can empty more blood in the left ventricle. So increases in stroke volume for athletes will result in a decreased heart rate. So ask your athletic friends what their heart rate is, and it wouldn't be uncommon for them to be under 60 beats per minute. Now, tachycardia, on the other hand, typically is going to be excessive sympathetic output. So if you were to measure the amount of circulating catecholamines, the amount of epinephrine, norepinephrine, going to be fairly high. So high heart rate. And typically you'll see people with fever, sometimes blood levels, if blood pressure drops, you're going to start to see heart rate starting to increase in order to increase the amount of cardiac output, or to at least normalize it. Other things that you can also see, typically related with high stress levels, high cortisol, hyperthyroidism. Give us an indication. All of these will give us an indication as to why the heart rate might be high. It's typically due to increased sympathetic output. Many reasons, but nonetheless, terms bradycardia and tachycardia are all related to the heart rate, the intrinsic heart rate. Now looking at the abnormalities. In the abnormalities, we'll be able to see the normal sinus rhythm. And normal sinus rhythm just lets us know that P, Q, R, S, and T are exactly where they should be in a normal heart. And looking at the normal rhythm, you can see right up at the very top in this antiquated ECG tracing, you can see that the very top represents the normal rhythm. And what this helps us do is to take a look at the heart blocks. Blocks are basically things that are a form of arrhythmia, and that arrhythmia is due to the lack or the dysfunction of either the SA node or the AV node, or somewhere along down the conduction system. So looking at what a heart block is, at least the first heart block, the first degree of the heart block is prolongation of the PQ interval. So here we expect P, Q, or S, and then T is P, Q, R, S, and then T wave. PQ, prolongation of the PQ interval due to refractoriness of the conductive cells in the AV node. All that's basically saying is that the SA node isn't firing as well. So looking at the PR interval, here let's take a look at, I believe, let's look at the junctional rhythm. So junctional rhythm, here you don't see the SA node. P waves, you don't see where the P waves should be. They should be over here, but they're actually masked. The length of the PQ interval happens to take place somewhere during the QRS segment. So now that it's not taking place, all you're really seeing is the missing P wave. So all you see is your QRS and then your T. P waves are not actually seen. So therefore, if you were to take a look at the rhythm, you can see that the space in between, and each of the ticks on this ECG, which you'll be doing in your labs, each of the ticks right here will represent a certain amount of milliseconds. And all you need to do is determine the time in between each of these R waves, which will tell you the heart rate. Now the rhythm, looking at the junctional rhythm, the missing SA node firing, what that's going to do, since the intrinsic heart rate of the SA node is about 100 beats per minute, you'll notice that the AV node is firing at about 60 beats per minute. So therefore, you're going to see a longer period of time in between your R waves. Now, the second degree heart block, here you can see the second degree heart block. This basically is saying that the atrial depolarization that takes place, not all of them make their way over to the AV node. So SA node is firing 100 beats per minute. Every time it beats, it should trigger the AV node to fire, which is going to result in ventricular depolarization. Here in the second degree block, there's a block at some point. If I'm going from SA node to AV node to the ventricles, the block is taking place that's preventing the SA node firing to meet the AV node. So in the second degree block, here you'll see P, Q, R, S, and T. Great. That's taking place normally. Everything from here to here is normal. But notice this next segment over here. There's our next P wave, and there's no R wave taking place. So there's no ventricular depolarization. This next one, from here to here, these are okay. These are not okay. So here what we see is a one-to-one. The SA node fires, QRS, and then T wave takes place. The next P wave starts, the SA node fires again, nothing happens. The next SA node fires again, and you go through a complete cardiac cycle. The next one takes place, and that's missing. So this is resulting in sort of skipping beats. In essence, what's happening is the ventricle isn't getting triggered enough because of the delay, the block between the SA node and the AV node. The last one, basically what's happening in a third degree block, this is a complete block between the SA node and the AV node, where the SA node is firing and the AV node is firing, and it's just firing at mismatched times. So what that is going to end up doing, atrial and ventricular contractions are taking place at different times, and it results in atrial as well as ventricular muscle cells firing independently from one another. So this is where typically you would get a pacemaker installed in order to get the SA node to start firing again. Looking here, you'll see ventricular fibrillation. This is basically saying there's no pattern to the ventricles firing anymore. They're just kind of firing at random rhythm. It's a little chaotic. It's spread out all over the place. You might still get some blood flow, but it's not efficient. You're not getting efficient cardiac cycles taking place. So typically in these situations, you would need to get a better heart. So that sums up. We're going to move on to blood pressure. I just at least want to take us through somewhere around cardiac authorization before we can take our stop for the day. Now, looking at blood pressure, I'm going to just touch on blood pressure because we're going to, again, talk about this in our vessel lecture. Blood pressure we've been looking at, it's all going to be related to being able to measure pressures that are taking place from ventricular diastole, which we see the pressures in the vessels on the output of the heart, the aortic pressures. We want to measure the fluctuations in diastole as well as what's happening during ventricular systole. So the pressures we want to measure are going to be in the aorta. And really, if I want to really be able to determine what the pressures are, that would be mimicking the information that's being sent out by our baroreceptors, would be to stick something into the aorta and measure the pressures. I would get a balloon in there and I want to say, okay, these are the high pressures and these are the low pressures, our systolic pressure and our diastolic pressures. Maybe not really the most, probably a little too invasive. So instead what we can do is measure the pressures close by. So what we can do is to, instead of measuring directly in the aorta, we can measure the pressures downstream, down an artery. And the typically place that would be the easiest would be to measure the pressures taking place in the brachial artery, since it's close to, pretty much in terms of pressure levels, close to that of the aorta. So here we can measure the pulsations, the pressures that take place. And we would do this with utilizing a sphygmomanometer, which is going to measure the pressures taking place in the heart. Again, I'll talk about that in the next, in our vessel lecture. Systolic pressure is going to measure the highest pressure, which is during ventricular systole. The diastolic pressure is the lowest pressure during ventricular diastole. And again, that represents the highest pressure for ventricular systole and the lowest pressure during ventricular diastole. So we should expect the differences in pressure from 120 down over to 80. And those pressure changes that you're seeing that take place, you should be able to see. If I were to take a pressure sensor and place that in the aorta, you should be able to see these fluctuations that take place. And each time you get those pressure waves, each of those are cardiac cycles, and that's the ejection of blood. So that ejection of blood, you should be able to see the top, the highest pressure, which is about 120, bring us back down to our lowest pressure to about 80. So looking at the blood pressure over age, like I said, 120 over 80 is ideal. But what happens with aging is that our blood pressure starts to go up a little bit higher. So about 30s, 40s, you'd see maybe about 125, 130, over 80, 85. As we get a little bit older, it gets even higher. And that we'll talk a little bit more about in our vessel lecture. Not entirely important. Recognize that females actually have lower blood pressure than men. So it wouldn't be uncommon for women to have about 110 over 70. Looking at the next slide over, you can see what the normal blood pressure is. And when we see that where we spend most of that time in, if you were to take a look at the pressures during an entire cardiac cycle, you would see that we spend about, most of the time, at about 80 millimeters of mercury. The other time is at about 120. So the easiest way of looking at where the average pressure is not to do 120 plus 80 and divide that by 2. That's not how you figure out your pressure, the average pressure in the aorta. The best way of measuring what that aortic pressure is to utilize this equation. Okay? So now what we're going to start doing, especially in physiology, is start to use some relatively easy calculations. What we're doing is measuring the highest pressure, our systolic pressure, minus the diastolic pressure. So 120 minus 80, which is 40, divide that by 3, which is 13.3. So 13.3 is the number that I come up with. And why do I divide it by 3? Because about 2/3 of the time we spend in diastole, about 1/3 of the time we spend in systole. So divide 120 minus 80 divided by 3 and add that to your diastolic pressure. So 80, which is our diastolic pressure, plus 13.3 comes out to about 93.3. That is your mean arterial pressure. And that mean arterial pressure is going to be important because what we're going to be looking at is that pressure is going to get conducted all the way down. We need to have that pressure form move all the way from your aorta, all the way down to your capillaries, all the way back to your veins. Because what happens if that pressure decreases, let's say down to about, this won't probably be practical, but if you bring it down to about 40, by the time this starts to dip, and we'll explain in our vessel lecture why pressures start to decrease when we go from our arteries down to our capillaries, once we get down to our arterioles or capillaries, you'll notice that the pressure will be down to 0. And if we don't have any pressure down at the capillaries, how do you expect to get fluid exchange to take place down at the capillaries? So this is why it's an important measure. The mean arterial pressure is something that they want to be able to estimate how well blood exchange is taking place down at the organs and all of our active tissues. This is going to eventually drive the gas exchange that takes place on that layer. So as we see the pressures, we see our systolic pressures. These are measurable changes that are taking place in the aorta, the arteries, and again, something that we'll start to see as it decreases by the time it makes way down to the capillaries, venules, and veins. And again, we'll explore what's taking place in the capillaries at the tail end of our vessel lecture. We want to be cognizant of the pressures right in that area, because that's going to affect the amount of fluid that moves in and out of the capillaries, as well as the gas exchange that takes place. In the cardiac cycle, the thing that they do during the cardiac cycle, easiest way to be able to listen to the easiest way to at least derive normal function of the heart is to listen to the valves. So while we're not really looking at the pressures anymore, we want to be able to hear how the pressure, or at least how the valves are opening and closing. So what they do in a process we call auscultation is to listen to the heart. And what we're doing when we're listening to the heart is we're listening to the valves. And so if you've ever come in with anything, or you have a physical exam, one of the things they want to do, that a doctor wants to do, is just listen to your heart sounds. And the way they can do that is just place them in areas right below the second rib, to the left and right of the midline, and right by the fifth and sixth, in between the fifth and sixth rib on the left side. And that allows us to listen to the valves. So here you can see our tricuspid to the right, you can see our bicuspid to the left. We know that blood is being ejected from the atria, from the right atria down the right ventricle in this direction. So the best place to listen is not on where the valve would actually be. It's a little bit downstream of where the blood flows. If you were to take a kink in a hose somewhere, the best place to listen for any sounds in the hose is not directly where the kink is to listen downstream. It's going to be the loudest, and that's why they would measure the sounds away from the heart itself, basically where it projects. Same thing with our aortic valve. Aortic valve, blood is being ejected by the ventricle up towards the top right of our body. So therefore, they're going to want to measure a little bit higher up. So all in all, what doctors are doing, or nurses, or whoever is trained in auscultation, what they want to do is they want to be able to listen to the heart sounds. One of the ways they were able to do that before, prior to the use of stethoscopes, was to actually place, a doctor would place their ear right up on the chest and listen. That became a little invasive, especially for females. So what they were able to do was utilize a stethoscope. A stethoscope basically does the same thing, but it directs the sound directly into the cup, which directs that into the ear, so you can hear the sounds without actually having to be that close up. So with that came the stethoscope, and what they can do is listen to the heart sounds. And the heart sounds you should be able to hear are the lub-dub, lub-dub, lub-dub. And all of that is corresponding to the sounds of the AV valves and our semilunar valves. Now going through, on the next slide over, you can see our normal ECG tracing. P, Q, R, S, T. And what we're listening to are the sounds that take place. And this is something that the Wiggers diagram will also do as well, is I'll place these heart sounds. So listening to the very first portion, you get, we're not really looking at the atria, we're looking at QRS. QRS marks the beginning of ventricular systole, ventricular depolarization. And ventricular depolarization is the start of ventricular contraction. So if I've got my, and let me just draw a simple heart, and this is a really, really simple heart. If this is going to be my AV valve, and this is going to be my semilunar valve. The first sound I should be able to hear during the very beginning of ventricular contraction. Ventricular contraction involves the slamming of the AV valve. Remember, the very beginning, prior to all this, the PQ interval represents atrial systole. Blood is being ejected out of the atria into the ventricles. So ventricular filling. Once we reach QRS, That marks the beginning of ventricular contraction. So what's happening at that point? As contraction takes place, this closes. So this is going to be our lub. So AV valve closes. The second sound, as we get blood ejecting out, and here's our aorta. Blood is being ejected out into the aorta. There shouldn't be any sound in the first place. Blood is flowing normally through. Then, when the ventricle relaxes, which is marked during ventricular repolarization, is when we get the aortic valve to close, which is the sound of dub. So lub dub, lub being the AV valve, dub being the semilunar valve. That should at least tell us if the valves are working normally. So that tells us a little bit about it. That hearing lub dub lets us know if the valves are opening and closing. The other things that you would also should not hear are the sounds of turbulent flow. So take a garden hose and make sure it's completely straight, like a perfect garden hose, and put your ear up to it. What you shouldn't be able to hear, you shouldn't hear any sounds. Because smooth laminar flow just causes fluid to flow through easily. Take a kink to the hose and now listen to it, and what you're going to hear is you're going to start hearing a whooshing sound. That's the sound you're hearing. That's turbulent flow. Turbulent flow is the sound of water hitting that kink in the hose and spiraling all around in that area. That's the turbulent sounds that you're hearing. Turbulence in the heart is not what we want. We want blood to flow all the way straight through. Any sounds are bad. So what you should be hearing are lub dub, lub dub. Now, the turbulent flows, there's ways that we can have turbulent flows. The first way, first sound we would hear is what's called insufficiency. Insufficiency is the incomplete closure of a valve. So what sound do you think something should sound like when you narrow out, when you don't completely close a valve? It's kind of like the sound of whistling. Like if you purse your lips and create a small hole, you haven't completely closed your lips. If you completely close your lips, you can't really make a sound. But narrow out your lips and you get a whistle. So any whistling that you hear lets you know that a valve has not, oh no, wait, hold on a second. Stenosis, I'm looking at stenosis, sorry. Stenosis is the incomplete opening of a valve. So this is a valve slightly open. That's the whistling sound that you hear. Okay. Insufficiency is incomplete closure of valve. So while a valve should close all the way, the backwash of blood from the ventricle back over to the atria has this whooshing sound. So think about what that sound would sound like. If I were to have a valve open, I have the door open, I have blood rushing out. Once the aortic pressure is highest, you should slam the door completely, and that's the dub sound you hear. Now, if this doesn't close all the way, you're going to have some blood rushing back in, right? So that is what we call our insufficiency. It's the inability for the valve to completely close, causing a backwash. So what you would hear, if this were the AV insufficiency, you would hear lub, swish, dub. That swish is blood flowing in, lub closing, and then swish, blood coming back into the atria. If you heard lub, dub, swish, that swish is taking place after the semilunar valve closes. So that is, again, incomplete closure of the valve. Stenosis is the whistling sound. So if you were to hear a whistling, so a lub whistle dub, and all of that is listed out for you right here. A lub whistle dub is going to be stenosis of the semilunar valve. So lub whistle. So lub. That's blood squeezing through a narrow semilunar valve. If you hear lub whistle dub, that's blood whistling through a stenotic AV valve. Okay? So all of that is letting you know the sounds that are taking place in an abnormal auscultation. So for those of you that are pursuing a nursing degree or a medical degree or whatever degree that's involved in cardiac function, these are important things to listen for. And all of that you can get just from simply listening to the heart. Okay? Cardiac cycle. Cardiac cycle. Let me just leave with, yeah, I think that's about right. I know I kind of bombarded with you guys with a lot of information. We started off all the way from the cell, and we ended all the way at pressures taking place in the heart. So I know there's a big chunk of what you guys have to review. So hopefully I haven't gotten you guys too lost. I know where I lost you guys, but nonetheless, we'll revisit that on Thursday, and we'll finish up this lecture on Thursday, and we'll get into the vessel lecture. I may go in, for the vessel lecture, I may go in and have you guys cover some portions on your own. They're fairly self-explanatory, so read up on those ahead of time. They're not going to be extremely important for the purposes of understanding the vessel lecture, but I would still encourage you guys to review it on your own. Lastly, quiz on Thursday. Everything up to what we covered today. So stenosis of the valves, insufficiency, everything from the cells, cardiac cells, up to what we covered today. Oh, wait, no, I take that back, sorry. Including blood. So blood up to today's lecture. This Thursday, so 2 days from now. And, oh yes, the labs, you guys can take home. I'm going to post this up on Google Drive also. So if you guys want to take a copy, all it is just measuring heart rates.
The homework due today?
Homework, yes, turn in.
I thought it was due Thursday, because he gave it to us on Thursday.
Yeah, it was Thursday.
That's why I know.
Just kidding, Thursday.
Don't mess with me.
I forget my days. I realize all the time.
I was like, I'm almost ready, but then I